Next up, we have Liam Gridwood, and he'll be talking about the challenges for the ecosystem and companies when it comes to open sourcing historically closed source firmware for soundboards. So, give it up for Liam Gridwood.
Thank you for coming today. As was said there, this is, has been a journey for us to take closed source firmware and how to open source it. So this is not firmware when I'm boot firmware, this is audio DSP firmware. So I'm relatively a firmware newbie. I usually attend Linux conferences. So for me, I've been introduced to all the different aspects of boot firmware today. So I'm going to try and talk about audio firmware now. The mission of this is just to help other people who are considering open sourcing firmware. And that could be firmware for another audio DSP, or it could be firmware they have for their sensors, or any particular subsystem within their hardware. And I'm trying to inspire others and describe the challenges that we had and how we've overcome those challenges, or trying to overcome these challenges to make a successful open source project. Lastly, I'll also be introducing the architecture of the firmware as well. There may be some similarities to other firmwares, or to, you'll notice if anyone's familiar with Linux, there's been some similarities there. About me, I work for Intel. I'm a software architect there. I've been using Linux pretty long, since '94. I am the developer of the sound system subsystem for SOCs within Linux, and also for the power management IC subsystem in Linux. I'm relatively new to firmware. I've only been working on firmware since 2015 with audio firmware, but before that I'm pretty much an audio guy and a kernel guy. So what is Sound Open Firmware? It's really an infrastructure for developing audio processing algorithms, and on an agnostic hardware platform. So because Intel is the main sponsor here, it doesn't necessarily force soft to run on Intel hardware. One of the key decisions was to make this as generic as possible, so that you could run this on ARM as well, or you could run it on a TI DSP. There's nothing specifically within the driver or within the firmware that ties it to Intel. So the Dark Ages. So when I say the Dark Ages here, this is reference to not the medieval period, but to the darkness within the audio landscape prior to having open source firmware. So I've been working on audio drivers a long time, and I've been working with drivers that have had to talk to a DSP for a long time. And the biggest problem we always had was that this firmware team was usually located in another country, in another time zone, and they would go and write the firmware, and this firmware would be traditionally written for Windows, and they would give you this firmware release later on, and when you had to write the Linux driver for this, you had many questions. You had problems getting it to work, you had problems getting it to boot, you had problems getting high quality audio playback, you had problems hitting the PKIs for power, and this usually involved us lots of email discussions to this other time zone, and they would reply back. And to fix a simple bug, it would usually take you about 3 or 4 days. They would never share their source code with us. They kept it in-house. We would ask. They would often provide us with documentation. And this documentation obviously would never be as up-to-date as the source code. So this is just not with Intel, this is with my employment history before, and when I was consulting as well. You tend to always get a closed source audio DSP firmware. So changing course, let's look at why we want to change course here. So for audio, there is market drivers here, and we're getting a lot of customers asking for us to open source the firmware. We have customers who want to be able to use the audio DSP for general purpose compute as well. We have customers who want to customize their audio processing algorithms alongside with the use cases. So when Intel does a firmware for audio, it tends to have a set of requirements in mind. And those requirements may well suit very well to a laptop or a PC, but they might not be that good for a car or for a mobile phone. So having this open allows for the customization by the customer here. There's also a lot of growth in areas. I mean, an example at the bottom here is on the home assistance. So there's an awful lot of growth there. So having this open as an infrastructure provides help for the companies making those devices. What another driver was, well, the initial driver for SOF certainly was the Minoboard, and there's a Minoboard sitting outside actually. So the goal behind the Minoboard project was to provide a completely open source hardware, software, and firmware platform. And they had done very, very well. They had open sourced everything except for the audio DSP firmware. And so when they came to me and asked, because they came to me as I was the driver author, they came to me and said, Liam, how can we open source firmware for this? So my first look was to ask the existing firmware teams, and those guys were traditionally from a closed source environment, and there was a lot of pushback, this cannot be open source for various reasons. So I took it on myself as a one-man project to see how difficult it would be to develop a firmware for the Minoboard here. And you can see the characteristics of the DSP. It has a very, very small memory. It doesn't have 2 gigabytes of RAM like the Bay Trail CPU there. We're talking kilobytes of RAM. So there were challenges there. So this is the architecture of this DSP we're targeting here. You can basically see it's a single core, DSP core, and it has a couple of DMA engines, and the SSP ports on the right-hand side, those are your audio interfaces. So those would be for sending I2S audio out. There is instruction cache, instruction RAM, and in total, we're looking at 96K of RAM. So when you think about writing an application, when you say that to an application developer, 96K is too small for them. And even for Linux, you're never going to get Linux running on 96K of instruction RAM there. So it meant, starting a firmware from scratch here, and also to fit into this 168K data RAM. And so you have to fit your audio buffers in there as well. So that was quite a challenge there, but I'll come to that later, how we came to overcome that. The host, so this is what the DSP looks like, but there's this mailbox here, this is what the host driver communicates with the DSP. So the host driver basically sends IPC commands to and from this. So as well as providing a DSP firmware, we had to provide a host driver as well. I'm going to talk about the challenges here. So it wasn't just a case of writing firmware and testing and validating it. There was a lot more complexities involved. Number one, and Intel being a large organization, and I've worked at other large organizations before Intel, the number one challenge is political challenges. We found that, when you speak to colleagues, most were either strongly in favor of open sourcing audio DSP firmware, or most were, the most proportion of people were either strongly in favor or strongly against. There wasn't many people who were neutral. The people who were most strongly against were the current closed source firmware team. They saw this as a threat to their jobs. They asking about fears of disclosing IP, how we add value. But you generally have to be prepared for this, and you have to be able to speak to them and tell them there's no job fear here, and you tell them the benefits of open source. So now that we went down this path, these are the same people who are developing the open source firmware, and they're all actively, I would say, enjoying this because you've taken them from a closed source world, and they're really getting involved now with firmware on GitHub. The one thing I will say is that the quote from Margaret Thatcher at the bottom there, it's true, because you will have to be prepared to fight the same battle more than once to win it. And I'm still having discussions with colleagues about the benefits of open source firmware against closed source firmware. What did help me is, certainly have some code that you can share, you can demo, go to other conferences and talk about it. So I talked about SOF back at Plumber's Conference for Linux in 2017. For me, getting customers on side so you could talk about it, and then customers would eventually ask for it. The sales guys and the marketing guys were very keen as well, because they saw that as a way to enable customers. So it's all about, gather momentum within your own organization to do this. If I go into the technical challenges, usually when you're doing an application, open sourcing an application, the compiler is not a technical challenge, because you have these compilers for x86, for ARM, they're open source already. But our DSP runs on Tensilica ISA, and the problem here is that the GCC compiler can generate Tensilica code, but it cannot do any of the SIMD instructions. So when I say SIMD instructions, it's a single instruction, multiple data. So on Intel architecture, those would be things like SSE or AVX. So the Cadence compiler can do that, but the GCC compiler can't. Unfortunately, for an open source project, you do need to have an open source compiler, because you don't want to restrict anyone taking part. You want guys, hackers in their bedrooms to be able to write code. So Cadence were very good. They said to us, okay, we realize this is an open source project. We realize that you want to enable everybody. So they were very good, and they provided a free compiler for Miniboard. So you can go to the Cadence website and you can download this compiler, and it will generate all the SIMD instructions for the Miniboard target. We are actively working on getting this supported to GCC as well. So after we've got a compiler, we need to build an image, because a compiler will generate an ELF file. And unfortunately, you cannot send this ELF file to the DSP and for the DSP to execute that ELF file. You've actually got to format this ELF file into an image of the memory architecture of the DSP, so that the DSP can boot it. So we had to do that. So before we could run any code, we had to build this image builder as well. This is open source now as well. This is a tool called RImage. You'll notice at the bottom there, we have an unsigned image. I'll come to that a bit later, but at this point, we should be able to run code. We hope. But when I tried to run code, it didn't work. Now, I had lots of documentation, because I work for Intel, so I could read the documentation about Bay Trail. I could read the documentation about the DSP, but the documentation didn't contain the validated programming flows for certain parts of the boot and for the SSP ports, amongst other things. There was also no way I could connect the debugger or printf from this. So what I did was, QEMU had basic extensive support, so I had to extend QEMU to add support for our DSP into QEMU. And then I could take the closed source DSP firmware and run it on my QEMU model. And from that, I could determine the sequence it was using to boot, so I could validate my sequence against that. So I knew once I had QEMU running, the closed source running on QEMU, I could then translate that into the open source firmware, and then I could have open source running on QEMU. After open source was running on QEMU, I could take it to the hardware, the real hardware, and I could boot. So that was a big step forward. So you may have to do this, and this depends on whether, for Intel being such a big company, the people who did the closed source firmware, lots of them had left, lots of them had reorged into different organizations. So, and lots of them were working on other projects. So I did ask around a lot for help, but I found that people had left and people who were too busy to help me. So this was the quickest route, the path of least resistance. The next challenge I had was that after I could boot, I found that, oh, wait a minute, I cannot play any audio here. So I also had to then virtualize the host side, because I wanted to run the driver that was used with the closed source firmware on the closed source firmware within a QEMU environment. So I could send commands to the firmware in order for it to program the DMAs and to program the SSP ports in the correct sequence. Because I had the documentation, but the documentation didn't tell me the exact sequence I needed to program. So I did this, and what you can see here is a heterogeneous emulator. On the left-hand side is an x86 VM, so you can run Ubuntu there, or Chrome, or even Windows on the left-hand side. On the right-hand side is your DSP emulator, and you can run your firmware binary on that right-hand side. You can actually attach GDB to them both, which is very useful because then you can step through. I've got 2 GDBs there. I was at the GNU Tools Cauldron on Saturday and Sunday, and I found out there's new technology, which means you can have one instance of GDB now, connecting to 2 different architectures with 2 different images. So this will be in the next GDB release. So with this, I was able to fully validate my sequences, and once I had seen the sequences used by the closed source firmware, I could then play audio. But that was all good on Miniboard. Then the next generation of platforms came along, and they introduced code signing. So even though I went through all that pain and effort to be able to play audio on Miniboard, the next generation, this is with Apollo Lake, this is on the upsquared board, and there's an upsquared board outside for you to look at. I could not run any code on upsquared because of code signing. So the only people that had the key to sign were the closed source firmware team, who by this time wouldn't speak to me, and the OEM. But luckily the OEM would speak to me, so the OEM thought it was a very good idea. The company who make upsquared, they want to build a developer community around their hardware. So they took our public private signing key and they installed it on their BIOS image. So you can sign with our signing key, and you can run your firmware on upsquared. The signing tool we have is open source as well. So I know Travis was talking earlier on about Intel signing systems. Well, this is one that's already open source, and it's using public key cryptography 1.5 and OpenSSL to do the signing. There was an implication here as well, because we were using GCC. GCC I think above 5.2 has the GPL3 clause. And for those that don't know, there was a thing called the TiVoization clause. And this basically meant that GCC could not be used to build software that ran on signed systems without there being a means of signing the code. An open source means of signing it. So, we're fully compliant here because we have this system where you can sign code, but we've also given you the tools and the key to be able to sign it. The last challenge is probably something that everyone's aware of here, is to build a community behind your firmware, and we've seen many others. They have GitHub repos, they have websites, mailing lists, IRCs, wikis, and everything. We've done that as well, and we've moved to GitHub, and we've found with GitHub it's been very, very helpful for us. Well, I found that our team who are now the closed source team who traditionally worked on Windows, they were very, very hesitant about coming to work on a mailing list. They did not really want to be involved in a project where they sent patches on a mailing list. But when we said, okay, if we move to GitHub, would you work with us? And they took a look at GitHub and thought, okay, yes, we can work with that because it has a graphical interface, and all our developers are used to that. So if you need to do that, I would recommend that, because that then brings people within your organization who are maybe not used to open source, brings them alongside to help you. I've also had to educate them a bit as well, so that the team from the Windows side, they're very new to open source, so you have to go through the basics, things about releasing early and often. Don't do abandonware, don't do infrequent code drops. They were very nervous about accepting patches from other people because it wouldn't be validated, and you then had to explain how to build a CI system to cope with that. But I found once everything was explained to them, they were very much on board. So now we get to the stage where we're actually running code. Just showing the architecture here. So the driver, again, its driver is not tied to x86. There's nothing x86 specific in the driver. The driver can have multiple backends for sending the control data. So this plane here, this control data plane here can be MMIO, it can be SPI, it can be USB. It doesn't have to be a PCI device. So the driver can run on any architecture. We've even got an RTOS in the bottom there, and our driver is BSD licensed on GPL, so it could be copy and pasted if needed. On the firmware side and the right-hand side as well, we took a decision as well to have some freedom with the underlying RTOS. So at the moment, we have this thing called XTOS. Now, XTOS is released by Cadence, so that's the default RTOS you get with the extensor architecture. But some people don't want to use that. They want to use Zephyr, or they want to use free RTOS. So we're adding support for something called CMSys, which allows us to abstract that RTOS layer very, very cheaply, so that customers can then decide which one they want. It looks like a traditional firmware stack at the bottom as well. You have the platform drivers. At the top is our audio processing components. Now, some people ask us, how do you add value into open source firmware? The boxes here, these two here are value add. So because we've got a permissive license on the firmware, it allows companies to come along and say, well, I've got this great active noise cancellation algorithm, or I've got this great speaker protection algorithm I want to sell. So I don't want to open source it. I say that's fine. You can then integrate your algorithm, or you can ship it as a binary, or you can externally integrate it, and customers can then pay royalties for that. But you're not stopping any value add from stakeholders who want to, who live on the money they make from value add there. Drivers, again, it's a very standard driver architecture. At the top there is our integration with ALSA, with Linux. And way down at the bottom is our low-level parts of the driver deal with talking to the DSP. And this part in the middle, again, it doesn't have to be MMIO. It can be USB or SPI or I2C. The transport here is, the driver is pretty generic there. Just some history. So 2015 is when I started working on the project by myself as a skunkworks project. So I knew, my manager knew, and his manager knew, and pretty much nobody else. Then, things gathered speed. We had working code on Bay Trail then, we had QEMU support, and we got Cherry Trail and Braswell supported. And then at this time, the closed source guys heard about us, and they tried to kill us and everything. They tried very hard to do that. After about 2017, this is when we announced to the world via the Plumbers Conference, and by that time we had all the firmware running on the non-code signing platforms, so everything up to Apollo Lake. After we got our code signing done, then at the bottom here for 2018, this is when the closed source team joined us. So we went from a team of 1 up to about 20, 30 people now, all contributing to the firmware. So we can see now we're starting to have code for next generation devices as well as the legacy devices now. So we're no longer a skunks work, we're an official project. And we have asks from customers as well, so which is very good. The development kit looks like this. So because we're releasing a firmware, you're not just releasing a firmware source code, you have to release an SDK. Because the tools are quite customized and specialized. So remember I talked about the compiler options here. So we have either the GCC or the Cadence compiler. We have the image tool and we have the signing tool. These are all open source. The one that isn't open source is the Cadence compiler. We have topology compiler as well, which is open source. So these parts are open source. So when I say topology, you typically in audio have a pipeline of processing from the source to the sink, and the topology is used to define that. So the team from the closed source world, they had a GUI which allowed you to do that, and it saved it as XML file, so we still support that. But we needed an open source alternative to allow the community to create pipelines as well, and this was all done in M4. Once you've signed the image, it then goes to the driver. We've got debug facilities as well, so we've got tracing and debug FS. So it allows you to inspect the whole DSP memory, the DSP trace events. We've got our emulation on this side as well, our Chemulon. Cadence also do an emulator, but this emulator again is something you have to pay for. The interesting thing, Google contributed this Docker support. So we have this option to put most of the SDK within a Docker container. And that's very, very useful because it allows you to deploy this container, because the firmware has certain dependencies on libraries and tools, and those are quite hard to deploy on your average Ubuntu system, because a lot of the dependencies are bleeding edge. For example, the topology compiler depends on bleeding edge ALSA-lib and bleeding edge ALSA utils, which are not yet released into a package which Ubuntu or Red Hat can pull. So you don't want to update your desktop with a bleeding edge one because it might be buggy. So you can do this all in this container. The container is very handy for CI as well, because you can run this as part of your CI. You can run the builds and everything. Again, this is the pillars of building a successful project. We've tried to have permissive licenses in everything we can. So in places where we haven't got permissive licenses, for example, our kernel is dual licensed. So for everything else, we've tried to be BSD or MIT. We've tried to make everything modular so customers can take out parts they don't need. We've been modular in that respect, so that you find that some customers have their own special algorithm and it can take up more memory and they want to ditch some other algorithms or some other code. That's all doable. Portable, we're not tied to any particular DSP architecture. We're not tied to any particular Intel product. And tool-rich as well, we're trying to provide as many tools as we possibly can, because going through the bring-up myself, I found that a lack of tools was a problem, and I needed to write a trace tool, I needed to write an image tool, I needed to write a signing tool, and emulation tools as well. So it was because those tools were useful for me, I thought they'd be useful to other people as well. And thanks, and please drop by the booth.